Welcome you all to this new lesson of circuit theory. Today we'll be discussing about Norton's theorem. In last two classes we discussed about superposition theorem and then we discussed about Thevenin's theorem. Superposition theorem, Thevenin's theorem, Norton theorem, all these theorems serve same purpose. All these theorems are used to determine current through a particular branch or voltage across a particular branch. But as I repeatedly said in last few classes that for some circuits, superposition theorem is suitable. For some circuits, Norton theorem is suitable. For some circuits, Thevenin's theorem is suitable. So under this module, we'll be discussing about different theorems, and those theorems will be applicable based on the circuit configuration. So today we'll be discussing about these three topics: statement of Norton theorem, its explanation, and later we'll validate the statement and explanation of this theorem by using some numerical. So what is the statement? Any active bilateral linear network which is having two terminals can be replaced by an equivalent circuit consisting a current source IN in parallel with a resistor Rn. So in case of Thevenin's theorem, any active bilateral linear two-terminal circuit was replaced by an equivalent circuit which was termed as Thevenin's circuit. Now in case of Norton's theorem, any active bilateral linear two-terminal circuit can be replaced by an equivalent circuit which is termed as Norton's equivalent circuit. For Thevenin's equivalent circuit, it consisted a voltage source which is having VTH magnitude along with a series resistance of RTH. But in case of Norton's equivalent circuit, it consists of a current source IN in parallel with a resistor Rn. So Thevenin's theorem and Norton's theorem are more or less similar as per the procedure. In case of Thevenin's theorem, any network, complex network, can be replaced by Thevenin's equivalent. By using Norton's theorem, we can represent any complex circuit in terms of its Norton equivalent. Thevenin's equivalent circuit consisting a voltage source of magnitude VTH with a series resistance RTH. In case of Norton's equivalent circuit, it consisted a current source IN in parallel with a resistor Rn. Now what is IN? In case of Thevenin's equivalent, after removal of load, the open circuited voltage will be VTH. In case of Norton's equivalent, the short circuit current or Norton's current will be how to obtain? First, remove the load. Now short circuit the load terminals and find current through that short circuit terminal. That is Norton's equivalent. RTH or Thevenin's equivalent resistance and Rn, that is Norton's equivalent circuit resistance, both are same. So I'm not going into details of that. So this is the statement of Norton's equivalent, Norton's theorem. So Norton's theorem states that any complex network which is active bilateral linear two-terminal network can be replaced by Norton's equivalent circuit consisting a current source of IN with a parallel resistance of Rn. How to find Rn or IN, that we'll be discussing in next slides. So let us come to this. So here we'll be discussing about the explanation of the statement. See, first step is identify and mark load terminals. So in case of Thevenin's theorem, we also identified and marked load terminals. Then we removed the load and found VTH. Here what will we do? Here this is the change. After removal of load, will make short circuit of the load terminals. In case of Thevenin, load terminals were kept open circuited. In case of Norton, load terminal will be shorted. While load terminals are shorted, we have to find short circuited current IN or ISC through short circuited load terminals. So suppose this is the given question. Suppose we are asked to obtain Norton's equivalent circuit for this one. So first step is to do what? We are asked to obtain Norton's equivalent for these two terminals. Now, as per Norton's equivalent, what we need to do? We first need to find IN or ISC, which is short circuited current. Now, A and B terminals are load terminals. As per step 1, short circuit the load terminals. So load terminals are shorted. Whenever load terminal is shorted, a current will start flowing through this path. That current will be Norton's current or short circuited current, ISC. Okay, so this is Norton's current. Now let us move to step 3. Okay, before moving to step 3, let me tell you, to find IN, you may apply current divider rule, mesh analysis, nodal analysis, whatever you want to apply, you can apply. But your objective is to find short circuited current through the load terminals. Next, determination of Rn. So to determine Rn, we'll follow the same steps as determination of RTH. So as like Thevenin's theorem step, for independent sources, you'll have to look back into the network from open circuited load terminals, keeping all sources deactivated or replaced by their internal impedance. So this is the given circuit. If we are asked to obtain Rn, that is Norton's equivalent. So what shall we do? We'll look back into the network from open circuit terminal. That means suppose you are at point A, you want to reach at point B. So how can you reach? You must follow this path. When you come to this point, you will have one path. This is one path to reach at this point. Suppose this is X point, this is Y point. So to reach at Y from X, you have two paths. One is shown by this red line, another is shown by this blue line. Now, these are two different paths to reach at Y from X. So these two paths are parallel paths. So Norton's equivalent resistance Rn in this case will be eight, 4, and bottom 8. These three are in same path, so these three will be in series. With this series combination, 5 is in parallel. Isn't it? 5 is in parallel. So this is how you can determine Norton's equivalent resistance. Now for dependent sources, what shall we do? We'll first find VOC from these open circuited load terminals. Then we'll find ISC, which is found in step 1. And then we'll divide these two to find RTH or Rn. So Rn or RTH, both are same. Okay. Now, as I said, why we need to find ISC or IN? Why did we find Rn? Because the given complex circuit, this complex circuit can be represented by this Norton's equivalent circuit. This is the simplest one. This Norton's equivalent circuit should consist of current source of IN magnitude with parallel resistance Rn. Now, any complex circuit can be represented by Norton's equivalent circuit, in which IN will be the Norton's current and Rn is Norton's equivalent resistance. So once this is found, so at the last stage, what shall we do? So as per step 4, replace the given complex circuit with load removed. See, load is removed still by Norton's equivalent circuit comprising this. So this is Norton's equivalent circuit. At the last step, what will you do? We'll reconnect the load resistance RL. So once load resistance RL is reconnected, we'll find IL through this load resistance. So formula for IL can be found by using current divider rule. So total current IN multiplied by, we are finding current through RL. So which one is opposite resistance, RN or RTH? Divided by RL plus RTH. So this is how you can find current through load resistance using Norton's theorem. Now let us validate our explanation and the statement with the help of this numerical. So here we are asked to obtain Norton's equivalent circuit. For this circuit, obtain Norton's equivalent circuit. That is, we are asked to obtain IN and RN. Okay. So how to find IN? To find IN, first we need to short this. So here we have shorted this. Now we have applied mesh analysis. We have considered these two loops, one loop 1 and this is the loop 2. Now why did we consider this outer loop? Why did we consider this outer loop? Anyone? See, here the concept of short circuit will be applied. See, this is one terminal, this is another terminal. Okay, now due to this source, forget about this part, forget about this part. Due to this source, a current will start flowing through this path. When current comes to this point, current will get this path to flow. And current will get this path to flow. Now, this is A point, this is B point. Now from A to B, current can flow through 5 ohm or current can flow through the short circuited path 0 ohm. So whenever current gets such two different paths, what current will do? Current will always follow the short circuited path, as this short circuited path is offering no resistance or zero resistance. So apparently current through this path will be 0. Okay, that is why we have considered this loop. Now, as this loop is considered, so applying mesh analysis, this loop or this mesh involves a super mesh. For this super mesh, I1 is this, so I1 should be equals to 2 ampere. So I1 is 2 ampere. Now if we apply KVL in this loop, what will be KVL equation? This is 4. So 4 I2 minus I1 plus 8 I2 plus 8 I2. So 8, 8, 16 for 20 I2. And for this branch it will be 4 into I2 minus I1. So minus 4 I1 will be here and minus 12. So this should be equals to 0. So this equation we have obtained by applying KVL in this loop. So from this loop, this is the KVL equation. Now we have found already I1 equals to 2. So substituting value of I1 here, I2 will be found to be 1 ampere. Now what is I2? This is I2. So I2 is nothing but current flowing through the short circuit path. So I2 should be ISC or IN. Okay. So this is how you can apply mesh analysis, or for some problem you can apply nodal analysis as well, or current divider rule simply to determine IN. Next target is to find RN. So how to find RN? See, as we already discussed, Rn to be found across these two terminals. So suppose you are at point A, you want to reach at point B. So you can follow this path to reach at B, or you can follow this path to reach at B. So see here, through this red path, 8, 4 and 8, these three are connected in series. So 8, 4, 8 are connected in series. With this series combination, this 5 is in parallel. So 5 is in parallel. So finally we'll get 5 parallel to 20, that is 4 ohm. Okay. So this given circuit can be replaced by Norton's equivalent circuit comprising ISC, that is 1 ampere, with parallel resistance of 4 ohm. So this is Norton's equivalent circuit. So this is how you can solve problem using Norton's equivalent circuit. Okay. Now let us solve this one. Again, we are asked to find Norton's equivalent circuit across these two terminals. So how to find ISC? First we'll short circuit it. Now, as there are two sources, we'll apply superposition theorem to find ISC through this path. You can apply what shall we say, nodal analysis as well here. Okay. So it's up to you which method you will apply. Okay, let us apply nodal analysis here. Let us consider voltage at this point is V. You can apply nodal analysis, you can apply superposition theorem as you wish. Suppose this is V. Suppose this is I1. Suppose this is I2. Now the entire I2 current will be flowing through this path. As this is shorted. So can we write at this node, if we apply KCL at this node, I1 plus 4 equals to I2. Now what is I1? 15 minus V divided by 3. That is I1 plus 4 equals to I2. I2 current is flowing through this path. So I2 current is flowing from V potential to 0 potential. So V minus 0 divided by 3 ohm. So 15 minus V plus 12 equals to V, or 2V equals to what? 2V equals to 27. So V equals to 13.5 volt. Now ISC in this case will be equals to, this I2 current is flowing through short circuited path. So ISC equals to I2. Now I2 equals to V by 3, that is 13.5 by 3. So 4.5 ampere. Okay, so this is how you can find ISC. Now you can also apply superposition theorem to get the same result. But for superposition theorem, this problem would be a bit complex. So that is why I'm telling you, sometimes you need to apply superposition theorem, sometimes you need to apply mesh analysis, sometimes nodal analysis as per your convenience or as per the circuit's need. So some circuits can easily be solved with superposition or nodal analysis both, but applying nodal analysis may involve less complexity regarding calculation. So it's up to you which rule you'll apply. So IN is found. Similarly, to find Norton's equivalent, RN is to be known. So for RN, we'll deactivate all the sources. So this is A, this is B, this is 6 ohm. These two are through 3 ohms. So 6 parallel 6 will be, RN will be 3. Okay. So this is how you can get Norton's equivalent circuit. Okay. Let us now move to this problem. Find Norton's current. Only Norton's current is asked to be determined. So what we need to do? We need to short circuit this and we need to find ISC or IN through this. Now, so whenever it is shorted, see, we can apply KVL in this loop. Okay. So applying KVL in this loop, current through this path will be 2 ampere. 10 minus 5i equals to 0, so I equals to 2 ampere. Similarly, if we apply KVL in this loop, that means this 4 ohm and 10 volt is parallel. So voltage across 4 ohm is 4ix. This should be equals to 10. So ix equals to 2.5 ampere, which implies this 2ix current will be 5 ampere. So 5 ampere comes to this point, 2 ampere comes to this point. So current through this will be 7 ampere. So this is 7 ampere current through this path. Okay. So IN will be 7 ampere. So this is how we can solve electrical network using Norton's theorem. So in next class, we'll be solving some more problems, especially on AC circuits. We'll be solving problem of Thevenin's theorem, Norton's theorem, or superposition theorem. So as of now, today I'm ending up here. Meet you in next class.